1, 2, 3, 1, 2, 3. Okay. Before we get started, thank you for showing up. If you have registered as a face-to-face, you are expected to come to the lectures. And if you only if you registered as online, then of course you cannot come to the lecture. You are from maybe even some other country. So we are going to enforce the attendance. So far, I have rewarded the attendance, but you could see that half the class is not showing up. And it's a matter of professional responsibility that if people have not learned the topic of that class, they should not really gain employment in the nuclear industry. In that case, there will be a hazard upon themselves, their co-workers, people who work under them, because they'll all be leaders and members in the public in general. You would agree on this. So in that case, if you don't come, if they don't come, you're safe here. But if they don't come to the lecture, we will not accept the assignments. So that will affect the final grade, obviously, in that case. Those who attended earlier classes will be rewarded. It doesn't seem that the reward option works very nicely. So in that case, they basically face getting an F grade if they do not come to the class. And that will be enforced starting the 31st of October. And thank you for showing up. You are responsible people, and I'll write you all reference letters when you apply for jobs. I don't know whether I'll do it for the other guys who simply think that they can get credit for a course when they haven't attended the class. All right, enough said here. I still am recording the class because university wants to create a library of recorded lectures and what they call Illinois media space. So I am abiding by the rules. We all have to abide by the rules. If there is a problem with the COVID-19, then yes, the attendance will be enforcement will be stopped. All right, so you didn't need to record that, Alvaro, but so it is recording now, I assume. So I'll share the screen, and you could go our safety class. We want to cover as many of the topics regarding safety, and you that would make you safety experts. Your salary definitely will go up by at least 20%. Because you would qualify both as whatever engineering discipline you're in, nuclear, mechanical, chemical, electrical, but also
as a safety engineer. Last time we have been looking at the phenomenology of nuclear reactor accidents. We consider the case of the loss of coolant accident. And in fact, that particular accident that we studied was a very simple ideas of conservation of mass, conservation of energy, and we are going to do that today. Conservation of momentum can describe really the situation that happened of all places in the 3 Mile Island accident. So we'll come back later on and study it like here in that chapter in full detail. Another interesting phenomenon that has happened regarding the safety of nuclear power plants is the concept of steam explosions. And you'll see that steam explosions has been recognized as happening in the Chernobyl accident, when we will go and describe it in more detail. But there is a suspicion that it also happened at the Fukushima accident, at least one of the reactors. You could see, as I'll show you later, that it was not just a hydrogen explosion. We know that hydrogen has been released in the Fukushima accident, as well as the 3 Mile Island accident. And as you know, hydrogen is very reactive with the air, so there have been definitely hydrogen explosions. But one of them was so remarkably similar to a steam explosion. Unfortunately, the Tokyo Electric Power Company, TEPCO, does not recognize that. So it is left for the designers and the people who do research to research it for better designs for future boiling water reactors. So today, we consider steam explosions as a possible kind of accident. And you could see that here we are going to deal with a very, very simple model. We don't need supercomputers. In that case, you need the supercomputer for more detail in solving the fluid equations, as well as heat transfer equations, as well as the kinetics or the reactor kind of time behavior in that case. All right, so steam explosions have been common in the chemical industry, particularly in the steel melting business. So after you use molten steel and turn it into an ingot, you want to quench that ingot. So you immerse the ingot of steel into water. And if it is not done gradually, a very high heat transfer rate occurs. And basically, you'll find that the metal interacts violently with the water. And we want to learn it is not like a chemical explosion of an explosive, but nevertheless, it generates quite a bit of energy. We'll see that in that case, the metal, very hot metal, shatters. It gets a very large surface area. The heat transfer rate becomes extremely large, and you get a deflagration, which is really an explosion. Not only in the metal industry, steam explosions have happened. They happened also in earlier days when they would manufacture bullets for rifles and for guns. So what they would do in Wisconsin, like their football team is named the Badgers, because those Badgers were the names given to the miners who would go mining for lead. And they basically had to burrow underground the same way as the animal that's called the badger. Then they melt the lead. And if you travel to Wisconsin, you'll find sometimes very tall towers. So from the top of the tower, they would drop the molten lead. And as they drop the molten lead, it falls into a bucket of water. As it falls, it takes the shape of a sphere and then is basically quenched in the water. And they have bullets for the early muskets. Not anymore, obviously. That is not the case anymore. In one of the situations that happened here on campus, in the chemical engineering department, it is very well known that one of the instructors were trying to show people what is in the word that's steam explosion. So he got a bucket of water in the front of the class, and he started pouring molten lead into it. The process became unstable, and basically he got a small steam explosion with water splattering students in the first row. So in a chemical kind of an experiment of that kind, stay away from the front row. I don't think the instructor would dare repeating that experiment before. So in that case, in the metal industry, steam explosion did happen when if you pour accidentally a molten metal. The molten metal in our case here would be the molten core. And the molten core would be the molten uranium dioxide plus the cladding, zircaloy, zirconium, with the spacers that are stainless steel, iron, mixed with the control rods material. The whole bunch of these metals all would be melted together, molten together, and in that case, we call it a corium material. Corium for core, reactor core, corium material in general. The rapid vaporization when the fluid comes into contact with another of a significantly different boiling point, it leads to a high rate of heat transfer. And in that case, it can lead to a deflagration, that's a terminology in gas dynamics, and then even to a detonation. So it becomes almost like an explosion in general. I mentioned here at the University of Illinois that molten lead situation. Liquid natural gas also was poured into water at room temperature, can lead to a detonation followed by a fire as the cloud of gas ignites. That's somehow what maybe what happened in the Fukushima accident, in that the interaction was between very hot steam, which is a gas in that case, with the cladding material on the fuel in the reactor core. And in that case, you get a reaction which is an oxidation. So let me see if I can write it here. If you want to produce hydrogen, one method in chemistry is to use steam. Steam is still H2O plus a metal. Let's say it's iron. And in that case, you get the iron oxide, and you end up with the hydrogen being released. Now, in the case of nuclear reactor, this is not iron. This is basically zirconium, because that is the metal with which we build the fuel elements. The same situation happened. You get zirconium oxide. Now, the zirconium is a metal, but the oxide is a powder. So you'll find that the cladding of the fuel starts falling off, like in the picture that we have seen last time in the last lecture. Check it out. That was the debris that are left. So hydrogen is released, and hydrogen is very reactive, and it has been released in the 3 Mile Island accident. It led to a very small pulse, but it seems that it has been much, much more serious in the Fukushima accident. All right, so we'll come back to this later. Notice that this is an oxidation type of a reaction. You can call it burning, because oxygen basically interacted with the zirconium. So we burned the zirconium in that case. If steam is at high temperature. One way of producing hydrogen, by the way, for maybe a future type of a transportation system using fuel cells rather than electrical batteries like the Tesla cars. Toyota in Japan is adopting the concept of using hydrogen and then using it with fuel cells. A fuel cell will reverse the reaction of what we call electrolysis. So another interesting reaction. If you get H2O and you circulate it with some heat and plus some electricity, you know that you can dissociate that water into hydrogen plus oxygen, but we balance the equation by adding 2 here, and 2 here. So in that case, we can use nuclear energy, electricity here, some heat too. You can use wind power, electricity. You can use solar energy, electricity. And in that case, you get the hydrogen. And the fascinating thing is that that reaction is reversible. So now if you take that hydrogen and combine it with oxygen from the air, you end up with back again steam. And in that case, you get electricity out back again. plus some heat. So if you use high temperature electrolysis here, that's another way of producing hydrogen. There is a third method using electrochemical processes like hydrogen sulfide. This is something that you study in the terms of a future generation of transportation system, that if you now use the hydrogen replacing the batteries, when you burn it or you turn it back into electricity, you are really producing back steam, which is not polluting like CO2 using fossil fuels in general. So a related process that happens here in Illinois at this time of the year, in fact, is dust explosions. Farmers right now, if you see them in the field, are generating lots of dust, harvesting corn and soybeans. You should just go out maybe south of the campus on the farm areas, and the combines harvesting corn and soybeans are making lots of dust. So when they deliver those soybeans or corn to the elevators, those big silos there out in the country to store it, lots of dust is generated. And then comes somebody and lights up a cigarette, or maybe starting an electric motor generates a spark, and the dust, only the dust, not necessarily any flammable substance, the dust from the corn or the soybeans has a very large surface area, and if you have a spark there, the dust explodes. So that's called the dust explosion. And I might show you some picture of those dust explosions if I have them somewhere on the website in general. It can lead to fatal effects, and people sometimes are not careful. The explosion could be so devastating that it destroys all the structures across from the roads from the elevator. Well, okay, so we said that steam explosion can happen in the steel industry. It can happen, it happened maybe in the time where there were maybe bullets for muskets. Natural gas could cause accidents. And the dust explosion in that case also are all forms of steam explosions that are more serious than the others. In the case of nuclear reactor, the molten mixture of the fuel, the cladding, the structural material that we designate as corium can leak from the bottom of the pressure vessel. In fact, that's happened in Chernobyl. They had a very bad design in that some of their cooling water was right there under the core of the plant, so that corium material came in, interacted with the water. A big steam explosion occurred that raised about 800 tons lid on top of the reactor, raised it up in the air, and then it fell down. I'll try to show you a picture when we study the Chernobyl accident. There is, as I said, also a suspicion that it may have happened in one, not the 4 reactors at the Fukushima accident. So how does the phenomenology, that's what we are after here before we go and study the explosions, the accidents per se, see what happened. Is it a loss of coolant accident? Is it a steam explosion? Is it a core meltdown? So let's see how a steam explosion would proceed in its detail. Initially, the molten corium material and water are separate. So you have now molten metal coming into the water. There is, in that case, a coarse mixing. And in that case, the corium material fragments into little pieces that are 1 centimeter in size. When the molten core, the molten metal, gets in touch with the water. And in that case, you'll find that there is large heat transfer now from the molten metal to the water without a pressure increase initially. The slow heat transfer is caused by the formation of an insulating vapor layer. So a vapor layer forms on top of the molten metal, and it insulates the heat transfer initially. However, with more mixing, you'll find that it needs, in that case, some trigger process. Just somebody maybe hitting the side of a cup would trigger the shattering of the cup if you pour hot water into it, because it would have thermal stresses in it. So you need the trigger process. It results from a localized pressure perturbation, as from impact, entrapment, or small localized vapor explosions. And in that case, it starts a shock wave. The shock wave may start at the surface of the vessel. Now that shock wave now interacts back again with the molten metal, and that propagating pressure wave fragments the coarse material that was 1 centimeter in diameter on the average into smaller size particles in the millimeter range. And the heat transfer area becomes so large that the heat of energy release turns into a deflagration, as it's called, and then a detonation. It becomes almost like an explosive in general. Just to get the orders of magnitude, the energy stored in the molten corium material is partially converted to the energy of the shock wave to the extent of about only 1.5%. We'll need that number for doing calculations later on. If all the fuel is assumed to react simultaneously in a pressurized water reactor, it is the same as the explosion of about 70 kilograms of TNT equivalent. TNT stands for trinitrotoluene, which is a high explosive, almost like putting an explosive, 150 pounds of explosive inside the core of a reactor. This is not a nuclear explosion, by the way. We have to emphasize that that's a physical or a chemical explosion. A nuclear explosion would release not 150 pounds, but 150 kilotons or more. It is suggested that the spontaneous bubble formations accompanies the shock formation and contributes to the high rate of heat transfer. Some people are still doing research on that topic. It's a very important topic. And that the fuel gets fragmented into small pieces by the shear forces in the shock wave. So if you have a shock wave, the shock wave acts like a piston, and in that case, you get an explosion. Early on in the history of the nuclear industry, there was a worry about this occurrence of steam explosions. So they run experiments, especially for boiling water reactor. And this is a fact that is not very, very well known for boiling water reactors and pressurized water reactor. And this is a graph from one of the papers related to experiments. They call them the borax safety experiment on boiling water reactors. And the fascinating thing is that people predicted that that could happen in a boiling water reactor. And indeed, it did happen apparently in Chernobyl. So you see here that the power as a function of the time after the process occurs, you'll find that the reactivity of the fuel can increase the power of the reactor, say maybe 15 times the nominal power in a matter of 1/100th of a second. So that could be very fast. And in fact, here is a picture of those borax experiments here. And I'm showing you those pictures here from a video. I took these frames one at a time. They had a reactor there in the outside in the country, maybe by Idaho Falls. That's where they run. The Idaho National Engineering Laboratory runs the safety experiments. And then they suddenly withdrew the control rod. So now the chain reaction became prompt critical, as it's called. And you could see the steam coming out from the cover of the reactor, moving up into the sky with those debris. Do you see the top of the reactor basically have been launched up into space, and then you could see this part here falling down. So it becomes an extremely violent reaction. I'll try to compare this later on with what happened in Unit 3, I think, Unit 3 in the Fukushima accident, and claim that I think it was more like a steam explosion rather than a hydrogen explosion. So you could see here the progression again of the borax experiment into a steam explosion in a boiling water reactor. And notice the debris there that was thrown up into the sky and then falling again. This documentation is from experiments ran out in the desert. Now look here, this is what happened at Fukushima. One of the units basically did not show up as a hydrogen explosion. Definitely here, it is more, Unit 3 actually was a steam explosion. Now look at the similarity, it's amazing that even the debris here. This is in the experiments on the borax experiments, and it repeated again. This is a reactor building in that case. Here is a periphery. These are the chimneys, and the top of the reactor basically was ejected up in the sky, and it fell down on the side. So it has all the indication that it was a steam explosion. Somebody should adopt it as a thesis topic and become very famous studying it. So this is I'm saying possible because the TEPCO, or the Tokyo Electric Power Company, does not acknowledge that it was a steam explosion. They claim that it was a hydrogen explosion, and that is not true, as I'll show you later on. It seems that the steam explosions do not just occur in reactor accidents, as we are describing here. They do also happen in volcanic eruptions. So we can have models for analyzing and avoid. Why do you analyze it? To avoid it happening in nuclear power plants. But this is a steam explosion that's happening in the Kilauea. I think I have a typo here. That should be it is an E, but it shows as a seat. Kilauea in Hawaii, July 17, 2018. You could see the similarity. So a steam explosion happens maybe in volcanic eruptions too. All right, okay, we are engineers. So we try to understand physical phenomena by building simple models. I'm not going to use a supercomputer to study that. This is what one of you may choose it as a PhD topic. I'm going to use simply the laws of fluid mechanics and heat transfer. We suggested that fluid mechanics obey three laws. One is the conservation of mass. The second one is the conservation of energy. And the third one is the conservation of momentum. And then we have a fourth equation that relates the variables of pressure, specific volume or density, and the temperature or the energy release. So we are going to use a very simple laws of fluid mechanics: conservation of mass, conservation of energy, and conservation of momentum. So let us build a very simple model of a steam explosion there. Let us describe how much energy is released by the steam explosion. The energy released by the steam explosion is going to be equal to the mass of the fuel that is molten, in that case, in kilograms, multiplied into alpha. That's a fraction of the released thermal energy content of the corium material into from the in that case, it would be primarily not from the fission reaction itself, but from the decay heat. And beta would be the thermal energy of the fuel, the specific thermal energy, units of joule energy per kilogram. So if we take the thermal energy per kilogram of the fuel multiplied by the mass of the fuel in kilograms, you get joules, and the fraction of that energy available to us is alpha. Now let us assume that all that thermal energy now that is in the fraction of the core that has been melted has been turned into what? Kinetic energy. Why? Because here we could see that the material that's in the core, part of it at least, has been ejected up from the same way that a volcanic eruption would happen. All right, so in that case, we use the law of conservation of energy. We say that energy released in the steam explosion is going to be transmitted to the kinetic energy to a water piston that goes up from the core. And we can see it here happening. Do you see here how a piston is going up in the air, carrying the core material and whatever is on top of it? And here also in the experiments, a borax experiment, the stuff is being ejected out of the reactor core. So let us assume then that kinetic energy released in the corium material is all transferred into kinetic energy of the piston that flies up in the air. And this is, as I said, is really a description of two famous accidents. One of them is the Chernobyl, actually also maybe also Fukushima, even though it is not acknowledged. And the third one is what's called the SL1 reactor, a small reactor that was built by the United States Army in the desert of Idaho. All right, so in conservation of energy, so here you could see that we are using a very simple model applying what we know about the laws of fluid mechanics, conservation of energy. You equate the energy in the fuel to the kinetic energy. So m alpha beta here becomes equal to half mv squared, and capital V becomes the speed of the piston flying up from the core of the reactor up into the air. Well, all right, so what is the speed of that piston now? It is not a vector, so obviously it's only, we call it speed because it's not a vector. V is the square root of 2e over m, and what is e over m? That is alpha, twice alpha beta, 2 alpha beta here. And we know that the speed, because we are using the joule unit and the kilogram unit, so that's SI system of unit, that would be the square root of 2 alpha beta m over m in meters per second. What is capital M? Capital M is the mass of the piston, and the small m is the mass of the molten material. So let us not confuse those two m's here. Here, this is a small m, the mass of the fuel that has been molten by a fraction alpha, and capital M is the mass of the piston, the water in the piston, and the speed there is V. Then, so what did we use here? We use conservation of energy. All right, so let us now assume that the piston rose up and hit up the top of the pressure vessel. So in that case, it's like throwing, say, a ball of mud on the wall. The momentum in the ball of mud or a ball that you hit the wall with is transferred from the ball back shared with the wall. And in that case, we apply not conservation of energy anymore, but conservation of momentum. So the conservation of momentum equation tells me that the momentum of the mass of in that capital M here is the mass of the water piston multiplied by the speed of the water piston should be equal to the mass of the lid on top of the reactor multiplied by the height at which the speed that it is going to go up in the air. And we see this here again in the picture where basically the lid has been shattered and thrown up into the air. In volcanic eruption, it would be lava obviously there. So mu then is the mass of the reactor vessel itself, and the phi is the vertical speed acquired by the reactor vessel. We can calculate that phi here, and we can tell what is the speed of the reactor vessel after the piston hits it inside the vessel itself. So in that case, we can solve equations 4 and 5, and we get that phi, the speed of the vessel rising up in the air. In fact, the whole vessel would rise up in the air depending on its mass mu, and that mu can be quite large. It could be 800 tons, like in the Chernobyl accident. So the speed would be capital M over mu. This is the mass of the corium material. V is the speed of the corium material divided into mu, but we got an expression for V at the square root of twice alpha beta M over M. So here we can calculate the speed of the vessel after it basically changes momentum with the piston that was going up in the air. And it's a very interesting relationship. The speed phi here would be in meters per second, 1 over mu. Mu is the mass of the vessel, the square root of twice alpha beta M, the mass of the fuel, and small m, the mass of the water in the piston. Now we go again and apply another conservation of energy equation. So you could see here how you can derive very simple models for very complex phenomena. Steam explosions are very complex, but we can get some insights into how to model them by being cognizant of the laws of fluid mechanics: conservation of mass, conservation of energy, conservation of momentum. Now that speed of the vessel is going now to raise the level of the vessel up in the air. We're not going to assume that it shattered like in the pictures that I have shown you, but the kinetic energy of the vessel would be half m, the mass of the fuel, phi squared, the speed that the vessel acquires after it's hit by the piston on its top. So it's half mu, and then you take phi here, this number here, and you square it, it becomes 1 over mu squared twice alpha beta mm, and that would be the energy in joules, since we are using the SI, or the System International System of Units. So we can calculate that the energy, kinetic energy acquired by the vessel is going to be that capital M over mu alpha beta m in joule. Well, again here, that vessel is going to rise up in the air if it is not shattered. And that happened in the accident that we are going to, at the United States Army, actually, reactor that they built to have small powered reactors for remote locations, like maybe provide energy for a radar in the remote north in Alaska or on Greenland or whatever. Or actually, they had a reactor in Antarctica near the South Pole. So that energy of the vessel is going to raise it up in the air. And that kinetic energy, that half mu phi squared here in the vessel, is going to be balanced against the potential energy. And the potential energy is the energy that determines the height at which the vessel is going to be risen. And we know that potential energy in that case would be mgh. So here is mu instead of m. G is the gravity acceleration. H would be the height at which that vessel is going to rise up in the air. And solving that equation here, we can determine the height at which the vessel is going to rise in the air. That's m, capital M, the core material mass, multiplied into the mass of the piston water, divided into the square of the mass of the vessel. You notice here that you have to continuously check on your units when you derive an equation. That's mass, 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 mass. Here I cancel. Alpha, beta are fractions, and then you have the gravity acceleration, and this is the potential energy, mu gh, that is the height at which the vessel can rise up in the air from the steam explosion. All right, so this is a nice simple theory here. It gives you some insight into, before you start using a supercomputer to try to get this is what you would call back of the envelope calculations. You get orders of magnitude. It's not going to rise millimeters. It's going to tell us that it's going to rise in meters. So let us plug in some numbers for a typical steam explosion. And I'll use really typical numbers from an actual steam explosion that we are going to study later on for the SL1 reactor. Usually the fraction of energy that from the decay heat that goes into the molten fuel is very small. It's about 3%. So our alpha is 3%. From calorimetry, some people suggested that beta could be 1.5 gigajoule or millions of joules per metric ton. When you say MT here, that's metric ton. The French ton or the SI system ton, try to remember, is 1,000 kilogram. It is different than the TON. So TON is the British or the American ton. They're pronounced the same way, TON, but the French are using, or the SI system of unit, this is the metric ton, and the French do not use one single N here, they use double NE, and it's abbreviated as MT. So that is a metric ton, and 1 metric ton is 1,000 kilograms that you need to remember, since it's preferred now in the profession, engineering and scientific profession, to use the SI system of units. The mass of the initial material that's in the molten can reach about 50 metric ton or 50,000 kilograms. You know that uranium is quite dense, 18.9 gram per cc. So we go to our equation for the energy release would be the 50 metric ton. Turn that magnetron into kilograms, you multiply into 1,000 kilogram per metric ton and metric ton cancel here. The fraction alpha is 0.03. The beta is 1.5 gigajoule per metric ton. We change the metric ton into 1 metric ton per kilogram, and then the gigajoule here Giga means billion. If it's megajoule, it would be 10 to the 6, but this is gigajoule, that's 10 to the 9th. That is a joule per gigajoule. And you find that that's quite a large amount of energy. Here is 2.25 billion joules, or 2.25 gigajoules. Remember, megajoule would be 10 to the 6, gigajoule is 10 to the 9. That's the American billion. The European billion is here what we call in the United States million. So don't get confused between the European, of course, terminology and the American terminology. The European also, when they write, instead of writing a period here, they use a comma. So we are using the American notation, if I dare say. So let's be aware of both of them, and we can use both of them. So let us say that the mass of the water piston is 10 metric ton. Notice that the fuel, molten fuel, is 50 metric ton, but amount of water in the water piston that is now rising up, carrying the energy from the steam explosion, can be calculated. We said it's V is the square root of twice E here, that E here divided into capital M. And you find that water piston travels at quite a high speed, 670 meters per second. So it's almost instantaneous. It rises up. And then if we take now the mass of the vessel, let us say that the vessel did not shatter like in the pictures that happened at the Fukushima. The vessel itself can be quite heavy, 500 metric ton of steel. That was the case in the SL1 reactor when we studied the accident. You'll find that the vertical, now notice because we applied conservation of momentum. Here the piston is moving at 670 meters per second, but the vessel itself is moving at 13.4 meters per second. If you know the speed of the vessel, you know its kinetic energy, half mu, the mass of the vessel, the 500 here, multiplied into the speed square, 13.42 squared. So you find that that vessel carries an energy of 45 million joule, of 45 megajoule. And the last step in the derivation that we did is that we applied conservation of energy again. We converted that kinetic energy into basically potential energy. And when you conserve it, you take the kinetic energy, half mv squared, and say that it is equal to mgh, the potential energy. This is an energy kind of a conversion process. You find that that vessel can rise 9.17 meters up in the air. In the case of the Fukushima accident shown here, you could see how the vessel, it was more serious than what I'm describing here. The vessel shattered, pieces of it are flown up in the air and thrown up. If you say that the height of that stack here, that basically aerates the containment structure. If you look, follow my, the arrow here, that's a containment structure of that reactor. Then you could see this is 100 meters. It throws up all those heavy parts, tons of weight, about 200 meters in the air before they started falling down. That also happened in the borax experiment, as I told you here. You could see the same situation happened. The top of the vessel shattered and flew up in the air. In the SL1 reactor, though, that didn't shatter, so our model applies more to the SL1 reactor than it applies to Fukushima, and it's left for some of you maybe to analyze what happened in Fukushima, regardless of what the TEPCO or the Tokyo Electric Power Company is telling us. Two very simple conclusions come out from that analysis. Steam explosions are thought to have occurred in the SL1 reactor, so we are going to have a description of that SL1 reactor in full detail, and that prepares you for designing better and safer nuclear power plants in the future, or operating them at least safely in our historical times. I said also that definitely it happened in the Chernobyl accident. I'll show you why we can say that when we analyze the Chernobyl accident. And possibly because, again, it's not acknowledged. It needs to be studied thoroughly. Nobody has studied it in full detail. Only in those lecture notes that I have here, I claim that the Fukushima accident I have a typo here in reactor unit number 3. So I'm giving you a few numbers here, and to plug in the numbers in the equations that we derived to basically model in a simple analytical way, applying conservation of energy, conservation of momentum to describe a typical steam explosion. If we go back later on to the Fukushima accident, you'll find that the steam, the hydrogen explosions that I mentioned here did occur, but they propagated horizontally. Whereas that steam explosion, as you could see here, because it had much more energy, it shattered the top of the reactor, broke it to pieces, and drove it up about from 100 to maybe 200 meters up in the sky. So it was a much more serious accident at Chernobyl, but people who designed boiling water reactors ran experiments because they were worried that it could happen. Unfortunately, the designs did not take it into consideration in that case. So in the future, we are going to build better fission reactors that will not cause that type of an accident. Later on, I'll describe to you the Arriva. Arriva is a French company, and they have built 2 units, one in France and one in Finland, of what they call the European PWR or EPWR. Some people call it an evolution. They call it evolutionary PWR. So in that case, the design gets a big pond in the front of the reactor, where if that situation happens or the core material is molten, they disperse it in a pond so that it can lose its heat up through radiation with the air. So that's the only design in the world that takes that possibility of corium material interaction with water. And this is a phenomenology of a possible phenomenon that can happen in reactor accidents, steam explosions, and we'll study it in more detail when we look at, let me maybe show you how it displaced the top, 800 tons top of the reactor in the Chernobyl accident, and later on we'll see what it did in the, oops, I went too far down. I hope I can find the picture. No, not here, not here, not here. I think it's near the end. We'll study this. Basically, that's the top of the reactor here. That whole area was thrown up in the air, 800-ton lid up in the air. It can be very, very dramatic in terms of the phenomenology of the accident. Oh, here it's shown here. Do you see here? Upper biological shield, a bad aspect of the design in the Chernobyl. That's a design flaw, we can call it. Nobody should build that in the future. They had the core region here. The core region melted. It had graphite. The graphite basically burned, and the steam explosion that happened threw up the lid of the reactor, upper biological heat up in the air and then back down. And the bad aspect of the design, look here, this is the reactor core that melted, and below the core they had water for their cooling system. So they should modify the design and show it more like with the corium material here interacting with the water under the accident. So we keep studying specific accidents after we build up the basically the phenomenology of accidents in general. And thank you in that case for your attention.